Good evening.
Good evening. I'm Apoorva, and this is week 8 for Stochastic Control and Communication. So, this week the focus was on Kalman filtering and belief state formulation of the POMDP problem. So, before we get into that, let's first take a quick recap of what was done last time because it's building on everything that's been done so far. So, last week we talked about we started with the idea of what is the meaning of sufficient statistics, but we didn't get into anything further. Sufficient statistics is a term that will come up in this week's work. So we started out by saying, okay, suppose we have a linear quadratic problem with some noise. We did not define or any specify what kind of a noise it is. Then we said that any typical problem any typical POM-DP type problem or problem with imperfect information, wherein our value functions j, k would depend on some information available up till time k. We saw that the formulation simplifies, and this was the final takeaway that if we are working with a problem with imperfect information, specifically LQ problem, then the optimal control is the same optimal control that you would have gotten. At least this part would be exactly the same as compared to a problem without imperfect information, meaning where there was perfect information, there also we would have gotten the same L. The controller component would be exactly the same. In fact, if we remove noise also from here, so if we go to the LQ problem without any noise, in that also this ln term or ln minus term or lk terms are common in all of them, meaning we could find the what the controller does by just looking at an lq problem without noise. Adding noise changes it slightly. If this becomes a problem of imperfect information, then instead of having a dependence on the information itself, we have dependence on something that is the expectation of the state given whatever information is available up till that time. This tells us that solving for this part and this component can be done separately, and this was shown in the form of a diagram that this is the controller component and this is the estimator component. Then we further talked about how are these estimator components generally dealt with. Hmm. Yeah, so the controller component and the estimator component. Okay, then we saw a couple of examples. Hmm. Then we came to the idea of filtering. Filtering meaning finding the estimation or finding what this is. We saw that this the filtering problem can be converted into again another optimization problem where the optimization function is trying to minimize some mean square loss, and depending on what information is available and using that set of information or that set of observations, what at what time you're making your next step, at what time you're solving this optimization, that defines the problem class. So the focus for us is filtering, which means we are looking at whatever information is available till time k, and we are making a prediction about time k itself, or rather it's not called prediction, we are making an estimate about xk at that time itself. We're not making a prediction about something in the future or something in the past. So it was said that the solution to this optimization problem, the minimization of mean square error, turns out to be exactly the estimation quantity that we want to find. And this quantity is something that has a few properties. One of those properties is that it is an unbiased estimator. Unbiased estimator means if we took another expectation over this, it would reduce to just the expectation of xk, meaning this term will go away. And this is something that will be useful when we talk about the belief state formulation. Another thing that was the core point made, that it's this term that can be computed recursively. And to compute this term, there was a particular theorem that came up. This theorem, you can think of this theorem as a variation of Bayes' rule applied step by step, and the proof we know is fairly straightforward. Okay, then we took another example. That example is not the focus right now. So what we saw was, the in the control problem, there is the controller component and there is the estimator component. And the estimator is basically trying to find what is this guy. And there's the rest of the process happening. And there is a separation between these two, specifically when we are dealing with LQ type problems. So now we're going to focus on the estimator itself, and we're gonna take a specific case when we talk about the estimator. So this particular version is called Kalman filtering. So Kalman filtering is for a specific situation when the dynamics, the dynamics is still the same, it's a linear dynamics. This is the dynamics. Here, this is the noise component. Then the observations are yk plus 1, which are some ck, xk, gk, uk, and some vk. Here, these two are the noise components. They still have the same property as before, that these noise components have mean 0, they're independent. But when we are talking about Kalman filtering, there is another thing that happens here. We are assuming that these two are Gaussians now. These are both Gaussian noise. So we can take a particular form for them. So let's say wk is sampled from a Gaussian with mean 0, and we can take the covariance to be some qk. And similarly for vk, we are assuming that this is again sampled from a Gaussian distribution with mean 0 and has some component rk as the covariance matrix. Apart from this, we also assume that the initial x0 is also a Gaussian. Let's just put it as some x0 hat and some Gaussian with some mean and variance. Okay, so now the whole idea of Kalman filtering is to find two things. It is to find what is xk plus 1 given y12 k plus 1, the same step. So here it could be k, here it could also be k. And this we know is just xk and probability xk equal to some x and y going from y having observations from 1 till k. And this is some continuous distribution, so we'll just take integral over dxk. We already know of how to handle this. This was previously labeled as pi k of x, and we know we can calculate this recursively. The recursive formula still holds. Now that we are dealing with Gaussians, the recursive formula actually becomes easier to handle, and for that there are some properties of Gaussians that come handy. Is this okay so far?
Yeah.
Okay. So next thing to notice is that the property that comes up is called jointly Gaussian. Hmm. So what does it mean for something to be jointly Gaussian?
The joint distribution is a multivariate Gaussian distribution.
Sure. So that's the straightforward part. Like suppose we have x and y as some distribution, some random variables. So if these are two random variables, then the joint, we want it to be some Gaussian with mu and sigmas. So what are the properties that can lead to this? So first, simple cases. Suppose x and y are both already Gaussians with some, let's just say if they're both already Gaussians, then what can I say about the convex combination of them? Or maybe not even convex combination, just some linear combination of those two.
Yeah, will be Gaussian.
Will it always be Gaussian?
Should be, because okay, x and y are independent.
I didn't say that, right? So
Okay.
that's why these properties are supposed to be taken a little carefully. So in general, this is like saying I have two Gaussians. Since I've not specified anything, they can be related. They could have some dependence on their covariances, uh, their means, and so on. So it could be something like there's one Gaussian here. Assume this is actually a Gaussian, and there's another one here. Then some sort of a combination, some linear combination of those two may or may not be a Gaussian. It could always happen that it is something like,
Oh God, Gaussian mixture models are this only.
yeah, exactly. So some sort of a mixture. This is no longer Gaussian. This is still like a rough diagram, but this is not Gaussian. So it doesn't mean that they're always Gaussian. So if that is not happening, then we can't say anything further. This doesn't always have to be Gaussian. You're right. If the previous thing is as it is, so if x and y are both Gaussians and independent, then this linear combination is going to be a Gaussian. And the way to argue about this, an easy argument would be just take xy to be on uh, two independent axes. Then the joint will be a Gaussian in a higher dimensional space. And okay, yeah, right. So now we're coming to the main property. So the jointly Gaussian property basically says if ax plus by for all ab is Gaussian, then x and y, so here x and y are random variables, then x and y are jointly Gaussian. Okay, so this property is going to come handy. We can see how exactly that will come up. So notice what we did with our three assumptions here. We said x0 is a Gaussian. So that means x1 will be some linear combination of this. So this component will definitely be a Gaussian itself. We're still trying to figure out what happens to the action. But if our earlier claim that we were making earlier was correct, then this is going to end up being something linear. So all this component is going to do is just shift the Gaussian mean, nothing else. But this component up till here is still Gaussian, and adding with another Gaussian, and since we are assuming joint, that this will be, oh, not assuming, we would basically be arguing that this is going to be something which is jointly Gaussian, then adding another Gaussian here would make the whole thing a Gaussian. That's the way the argument will follow. Okay, so this most of these arguments are going to be based on the fact that we're dealing with Gaussians, and Gaussians are slightly more easier to handle than other types of noise and so on. So with this type of a problem, then Kalman filtering says, the algo itself directly says, that at every step, this component, the p, this probability, this is the probability p x k is some value x given whatever information it has. So the information is basically k going from 1 to, y going from 1 to k. So observations up till k, all of those are visible. Then each one of these is a Gaussian with some mean and covariance. The mean and covariance will be the quantities that can be recursively calculated, and the exact form is as follows. And the process to do this, that's the core algorithm, and there's like, it's something which has been around, which has been established for really long, so there's not much to question here. Remember, when we talk about this type of a problem, there are two steps. The first step is the prediction step, and then there's the measurement step. In the prediction step, the information available is up till k. Using that, we try to guess what might be the state, the next state, which is what is written under this symbol. So it's x hat k1 k plus 1, knowing information till k. So this is whatever is our estimate of xk, or the mean that we would have gotten. Remember, this is the distribution. This is p xk. So we're just simply using the mean from here and plugging it back into the form of our dynamics. And now notice the way this is written is, the noise component is not going to show up in the estimate, because the noise is going to give us a mean of 0. So that part will not show up. If that was present, then the mean component will also show up, and anyways the problem would change dramatically. So this is first scenario. Next is, we need to have a prediction for the covariance also. So the covariance will get affected by, the covariance is just going to be taking a a transpose around the covariance and then adding the qk term. Remember, qk was the term that was present in the observation, had this component, right? A noise component. That's where the qk was. So that component came about here. The variance will get affected because of the noise in the observation, and this is the estimate of the variance. Next is these two together in the prediction step are creating again some Gaussian, and this is the mean and this is the variance of that prediction. Now this is to be used and the measurement step is to be calculated. In the measurement step, a few things will show up. The first thing is there is now the estimate of xk plus 1. Now since this is an actual estimate, a filtering thing, there's no given k term here, and to this we're going to use our belief about it, or whatever we think it should be, our prediction from the previous step, and then on top of that, with some some linear combination in front of it, will take the difference of the y, as in the actual observation and the estimated observation. And once we do that, what we get is the filtering step, like what will be whatever it is that we are actually interested in. This is, remember, this is the component that we're interested in, and we to get to this expectation of x k plus 1 given y starting from 1 till k plus 1, we're just trying to get the mean of our estimate. And since this is a recursive process, the recursion requires the following steps. Okay, next is we will use the covariance from the previous step, the prediction step, and use that to find the covariance in the current filtering step, the measurement update step. So this has the following form. Not much of an explanation required here because this is just some algebra that happens once you've used the required properties and so on. Notice the key component here is when we are writing the measurement step, it has two portions. One is just taking the predicted value of x k plus 1 and then only noting down the difference in the observation, the actual observation and the possible predicted observation. This possible predicted observation is something we would have gotten uh, in the following way. Yeah, it's written over here. It uses our estimate of xk plus 1, our prediction of that, and the step taken at that time. So this component is fixed. This is what we calculated in the previous step, and that is going to be used here. And ultimately, it's the difference between this and this component. One second. So, if you want to think about this as an algorithm, an iterative algorithm, that is perfectly fine, because we are given exactly what to do, what are the steps to follow, and if we follow those steps, we'll be able to get the next updates. And remember, the updates are both the things. We are getting the update of this distribution, meaning this quantity is equal to some x dash given by k plus 1. Right, we started from here, used the prediction step and the measurement update step, and managed to get the new distribution, the next distribution. And the reason, see, all of these, if you notice, are just some linear steps and nothing more is happening here. The linearity that you see over here, it's because we're dealing with Gaussians, and Gaussians have a lot of nice properties, and that's the reason why this is all happening. Okay, so far. So if you want to, get more accustomed to this, to get a better understanding of this, the next thing to do is pick an example and implement it. For example, I think yeah, I have one possibility for you to try out. So take the exact form of the linear dynamics and the observation. Take exactly whatever you want. So here in this process there are no actions. This is just some process. It's in fact called a Gauss Markov system. So once this process happens, there are going to be some estimates, since the noise terms are both Gaussian, and also the initial state is a Gaussian. So using something like this, you can try out and plot what happens to these types of quantities at different time steps. And to do this, to implement this, all you have to do is write the core algorithm of you have to just write the core algorithm of Kalman and let the next steps happen on its own. Depending on what is present and what is not present, you might have to simplify it a little bit. And here again, notice A and C are something that are not dependent on time, so this makes it much easier. In the suggestion here for the code, they are telling you to just randomly pick a matrix. You don't have to worry about this stuff. Just pick whatever matrix you want and see what happens. Then you can tweak that matrix A and see how does changing the matrix A changes the process, changes the estimates that we're getting, the Kalman filters that we're getting. And this simulation will allow you to have more intuition about how Kalman filters work. Okay, now I'll come back. Right, so this is the algorithm. Remember what we're doing here? We are interested in updating these pi k of x recursively. And to do that recursively in a setting where these quantities are all Gaussians, we just need to worry about updating the mean and updating the covariance. And to do those two, we divide it into two steps. First is the measurement step, and then is the first is the prediction step, then it is the measurement update. That's pretty much it. And one of the things that is used, one of the properties of Gaussians that is used, is called the Swiss Army knife. So this one basically has a particular form of how to go from the posterior to prior kind of a setting. In Gaussians it's much simpler. So if this is what we had, we know this formula holds, this is just the base rule. But if you know these two, you can find these two quite easily using just certain properties of the Gaussian itself. So let's say it had a specific form. Right, so let's say this is, so I'm writing the Gaussian in the following way. So this I'm saying is a Gaussian, so I'm writing it this way. This is the variable, this is the random variable uh, on which the Gaussian is defined, and then it's the mean and the variance. So let's say the mean is some Cx, and the covariance is R. This is one of the terms, and let's say the other term is again some Gaussian. This time it's defined on the random variable x and has some mean and covariance. Now, just writing this much, using just these terms, it is possible to write down what the other side of it will be. The other side will be y becomes c mu. So it used, so notice there's a, the x variable here is a part of the, is a part of the mean component. That's why the mean term shows up here. So it becomes c mu, and the covariance gets affected in this way: c r c transpose. Oh no, 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 no. C p c transpose plus r. And the other term, so this one, the one that I've written here, refers to the prior on y. The other term becomes, oh, this is a slightly longer one. These are things that you can, keep like a list of formulas, nothing more than that. You can prove them. They're not that difficult to prove, but you don't have to always prove them before using them. You can use it like a given formula to you. In fact, even I don't remember such a long formula. It's too long to remember. It's useful, but it's too long. So few terms come up here. There is k bar y minus c mu. Where m is mean plus
In this that marginal distribution of y, the what is c?
here.
These are conditional. The marginal in the that side, p of y is equal to small y.
Mm-hmm.
There is a c in the variance term.
Yeah, the p is this one.
C that
Ah,
c for
c
Canada.
is this.
C of x.
Yeah, there's
Okay.
some linearity on x, right? That linearity, that matrix shows up here.
Okay.
Uh, okay, and k bar is b c transpose. Fairly long one.
We can mention c is equal to c of x without x.
Hmm?
We can mention c is equivalent to c of x without with the non-dependency of x, something like that.
Ah. You want to absorb c in x itself? That's fine.
Mm-hmm.
This is just so that it matches the form that we're going to use. That's about it. So now, let's say this is given to you, okay?
One curiosity I have, okay, can I ask one question?
Yeah, yeah, sure. Tell me.
This thing, like suppose many of the time in real world, we don't have this luxury of taking Gaussian. So I got this idea, what if if you somehow, let's say, hidden variables or hidden states, the sum of that hidden states will be your x, and some of your hidden observation will be your proper observation y.
Hmm.
So I can apply center limit theorem and force to be Gaussian and then go to Kalman. Is that thought process correct?
Yeah, I think a lot of the times the things that you get from Kalman are used as an approximation when you don't have uh, when you don't have Gaussian noise, or when you don't have Gaussian in the system. Then you use it as an approximation, and then you put your update rule will have the difference that it's not actually a Gaussian. There might be a heavy tail if it's a different kind of a distribution. So people sometimes use it. It's a very strong tool, so they use it.
So they use as a Gaussian, like, or no hidden variable, directly as a assumption as Gaussian, and then derive it. Whatever comes, it's an approximation.
The
Oh,
approximation might need to be adjusted on top of it. So there might be an extra term to adjust. But up till two moments, it is still like okay to go with this.
okay.
Another way to think about this is see, just like you have Fourier transforms and Laplace transforms and so on, you can have
Mm,
Gaussian transforms. As long as your system, as long as you have joint Gaussians, you can have those joint Gaussians be used to define a transform, and whatever distribution you have in reality can be written maybe as a mixture of Gaussians or of the sort,
mm,
at least
mm,
approximated using some mixture of Gaussians, and that could be used here.
okay.
Each Gaussian system separately, clearly that will change a lot of the assumptions, but as a first step entry point, it can be used.
Okay.
I think that's
Thank.
partly why Kalman filters are so useful. They started out as a simple system that can be managed, that is analytically good and well formulated, but it gives some powerful insights that are useful in other settings also. May not be exactly correct all the time, but approximately they can be used.
One more, like, we need to forcefully fit into linear version. That anyway Taylor
Yeah,
series kind of approximation.
yeah. Linearity is the systems, the dynamics of the problem is linear. If the dynamics is not linear, then you're in a different type of a problem altogether. Then whether you can do all these things or not is not guaranteed.
Okay. Okay.
This is specifically linear quadratic. There, if instead of Gaussian noise you try something else, it there's a possibility it might work.
Okay. Okay. Thank you.
Yeah. Okay, so now one thing to notice is this is just based on the base rule itself, that we can write down what is this quantity. Suppose we take an integral over x, so all that is left is just the prior on y, so it gives us this quantity. This is just an artifact of this, what is this called, Swiss army knife of Gaussian's thing. This is just base rule, nothing more. One second. Right. And similarly, we could, okay, before we go to the next steps, another thing you could do is write this quantity. You could also focus on this quantity. This quantity can be written as these two and this in the denominator, meaning this is nothing but the long quantity, the probability of x given y. Okay. Okay. So another thing, if you want to verify that this is in fact correct, I'll just give the hint. I'll just say what the process is. You can try it out on your own. So write out both of these things explicitly. Consider these to be what is it called? Um Consider this to be a multivariate problem. Okay, then you know you're going to be careful about it. Then once you have written this, the exponential components together, all you have to do is you have to just complete the square, and in the process of completing the squares you'll see some terms show up, and then it's just manipulation and trying to match this side with this side. That's about it. So here, this will lead to some linear components of x also. So if you just complete the squares and with respect to x, you'll end up with this type of a structural breakdown. That's all about what is happening here. Okay.
Yep.
So if now we apply this particular property of Gaussians to our problem. So our problem was the Kalman filtering, and we had two steps, right? One is the prediction step, and the next is the update step. In the prediction step, our focus is on finding what this quantity is. And we want to do it recursively. So we do know the previous one, so meaning we know this one. Pi of k means, so this is the quantity that we are interested in. This one we know, and here we also know that this is a Gaussian with mean x bar k and variance sigma k. So this can be written as the Gaussian that affects this is just part of the transition probability. How do we go from xk to xk plus 1? That's about it. So this is the system dynamics part. This is the system description. And the other one is, what is the probability of this xk? Which is just pi k, this pi k that we already know. Oh no, not the, sorry, not this pi k. Right, this pi k, right. What am I writing? So this is xk bar. Okay, this is the system's information. This is some sort of a prior, or the previous information that we already have. So now here what we're supposed to do is, oh, okay, and the integral is over dx k plus, no,
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 no, no.
not k,
It
no,
should be
not k
on
plus 1,
K.
it has to be on k, right? We're using the previous information here. The previous
So
step is what we're using, right?
what I did is when I did this expansion of this one, the p of k plus 1, x p of x k plus 1, and introduce x of k,
Hmm.
then inside it is coming this, like first term system was coming p of x k plus 1 condition of x k and y of 1 to k, and
Hmm.
this side is probability of p of x k given
So
y k
this
plus
is,
1
so this term is something like p of xk plus 1 given
given x
xk.
k,
We can be
that
more specific.
x comma
K is the
that y,
realization here, okay? X is,
and then y of 1 to k, that anyway not different. Okay, fine. So this was coming k and then y of 1 to k, which is pi k.
mm, this.
So
Remember in the, one second. Remember in the transitions, we care about the next action, but we don't care about the observations.
yeah, yes,
Observations
yes,
don't directly affect it. That's why it has a form like this. Now
yes.
continue.
When I see in the lecture, the sir mentioned there's a system, but for system, transition probability has action, right?
Yeah.
So that is not there. So it just some
Yeah. It's
then
sort of like summed over, integrated over, and thrown out.
okay, okay. It's like loosely speaking kind of
It's
thing.
rough. It's a little rough.
Okay.
Okay. So now we can use what we had previously, right? We could use this and compare it to the version we have, and write down that this will turn out to be some n. This is notation right now. Oh, this is xk plus 1. That's the variable here. This is the mean, and some variance will show up. Okay. So now we can apply this particular property, the Swiss knife property, which tells us that this xk plus 1 will be, now from the comparison, c is this, and r is this is the mu. So what happens here is this becomes akxk bar. Okay. And then the next term is the following. Notice what happened to the next term. So this becomes ak sigma k ak transpose plus qk. Okay. Notice here the u term, the action term is not there, which is why that's not showing up anywhere. If action was present, that would have an effect. That term would show up here. Are you following what I'm saying? So if instead of this, if it was, okay, let's write it carefully.
Basically, dynamic equation, and you put expectation on both sides.
Hmm. Yeah. So here, if you include the action, as in take the conditional over the action, then the mean will get affected, meaning there'll be an extra term coming up. Hmm. Okay. Next is the so this was the prediction step. The point here is we started out by saying, more like an induction type assumption, that pi k is Gaussian. We end up getting this, the prediction step distribution, as a Gaussian with some mean and covariance. Next step is to understand what is the measurement step. Measurement update gives us something, and what is that? So the measurement update is, I'll just copy some of it, okay? No, I have not written it correctly. No, that's not correct. The update step has to allow for k plus 1. Right, in that case, what happens is this becomes phi k plus 1. That's the integral component, and this, if we are taking the conditional on xk, so this is the observation uh, distribution that we had, that is what is coming here, and there will be some rk plus 1 in the covariance component. Okay, so this, if I were to write it more carefully, this is probability of yk plus 1 given xk plus 1. Right. We're using, so we had this result. 1 second, what was the result? Yeah, we're using this now. So this is first step. Next is to use what we got in the previous step, the prediction step. So the prediction step is xk plus 1, and there's some mean and covariance. This whole thing, and then the integral over all of this. And the integral is with respect to xk plus 1 this time. So this is what is happening. So this is the update step. So and then the integral over this with respect to dxk plus 1. Okay, now we can use the Swiss knife result again, and there may be a bit of simplification required, but ultimately this is, see, this can be compared, this becomes our in our form this was also C but not CK. So this is going to give us some Gaussian over xk plus 1 with some mean and variance. And this mean and variance is something that we can write using the Swiss army knife of Gaussian theorem, which would give us so there is some k C. Remember, we're not worried about actions here, which is why the action terms are not showing up. Otherwise, in reality, this should have been y hat k plus 1 given k, which would have the dependence on u as well. And the covariance is going to be where this k bar is, this is going to be actually something that depends on k. This k bar is this is inverse. It's only when you simplify this a little bit, you'll see that this starts to match what the Kalman filter algorithm gave us. Difference being here, the u terms are not present, so you have to carefully include the u terms as well. Yeah. So this is something that you could try out. This is more like a coding thing, a simple coding example that you could try out to get more intuition about Kalman filters. By the way, here we took the case where the motion is simple. Remember last time we had taken a situation where we were talking about the dynamics of a cart moving on a road, and we wrote down the dynamics. We wrote down a simple linear dynamics. This was like a translational motion, and there was a force acting on it. The force led to some change in the velocity, and that was what was translated into action and so on. So it doesn't have to be restricted to a problem of this kind. It is possible to use ideas similar to Kalman filtering in situations where you have rotational motion. So maybe instead of thinking of the cart as just a box which is moving, you can think of the wheels of the cart which are also moving, and that is more like a rotational motion along with translation. So it's like a helical motion if you were to notice carefully. So those kinds of things can also be studied using Kalman filters. So there could be a dynamics, then the dynamics would have some observations made about the true state, and then on top of that, if you're trying to estimate what the actual state was given whatever observations you've made up till say a k point of time, then similar ideas are actually used. In fact, I have seen people using it in even more complicated situations where suppose you have um, rotational degrees of freedoms, and you have a satellite a certain distance away from, for example, earth, then it has a lot of motion. So it is moving. So if this is earth, it is moving around the earth, and it is also rotating on its own axis also. So it has two frames of reference to care about. It has actual movement, the translational component, and the rotational component. So all of that is also many a times handled using Kalman filtering as well. Like how to estimate the true state given only the observations. And the observation, for example, in the case of satellite, could be very different because you're in two different reference frames, the rotational reference frame of the satellite and the rotational reference frame of Earth itself. Those two are also not properly aligned. It requires proper alignment, writing it carefully, and then doing it. So, yeah, those types of examples are also where Kalman filtering shows up quite often.
I have two comments. I was seeing the Kalman's 1960 paper when he proposed his first prediction filter, and there he was not using this much complex version. He was using simple dual of the optimization, and he was able to get this result.
Yeah.
So how do we make this thing very complex? I don't know. Like, fine, we need to
So,
see history.
it's just that it fits into the framework of control problems also. Kalman filtering is studied separately also, just as a way of estimation. But because right now we're in a course about control, and control requires you to make estimates about certain things, like the expectation over xk given information up till k. So, because we have to make those kinds of estimates, that's when Kalman type work comes in. It doesn't mean that this is only the place where Kalman filtering works. It works in a lot of other situations also, other kinds of estimation also. But yeah, the
Mhm.
original paper was much simpler. It's just that it fits into another framework, which is the control framework. That could be why it looks more and more complex.
And second comment will be like, let's suppose if you somehow model as a human behavior as a Gaussian and climate change as a linear thing, we can make some kind of like climate change model with Kalman, something just thought. But anyway, solution we know already.
Yeah, I'm not sure how we can.
Because their information, the actual state is not known. We have imperfect information about the actual climate. We have some sensors or something,
Mm.
and human behaviors could be the action which is fixed. Noise, or maybe noise. The human behavior could be the noise in this formula, and then there is a state changing every year.
So where is the climate going? So you're basically saying, I don't know whether it can be modeled as a linear quadratic Gaussian model, but it can definitely be modeled as a control problem, stochastic control problem. In
because
fact, without perfect information.
because the heat cost I can take as a power. Let's say heat is an energy which is power of
Hmm.
quadratic form.
It
I
can be
can
in
consider
quadratic form.
that an observation will be like some particular places some observation is taken care, mostly democratic countries, and then the state will be the actual state which is unknown. I don't know what is the actual state,
Hmm.
and
It's the
then model like this. I just thought I just it came.
yeah. It's I think it's doable, and by human actions you mean whether we are trying to save the world, like uh, in terms of the climate change that is happening every year. You mean those actions, right?
Uh, no, not that. More realistic. For example, how much consumption we are doing of energy, or how much the fuel consumption, or like that action.
Oh, okay.
There is set of actions we can define. Like action number one is going down of the fuel size or fuel thing, and then say option number two will be more sustainable energy setup. Third will be some action. So set of actions,
Hmm.
then set of states. But those states are completely unknown. We don't know actual reality.
Ah, I think it fits into this framework. It can be modeled. What you can do with the model is not something I can comment on, but yeah, you can model it so easily.
Okay, yeah. Thank you.
Okay, so right, so let's sort of try and back up and summarize what we have so far. So remember, we started all of this because we know that in LQ problems, before I even go to LQG problems, in LQ problems, the optimal strategy or the optimal action has a form like this. So I'm talking about the case with imperfect information, okay? Now, this part is very well known. This is something that we've seen a lot. Now, if instead of LQ problem, if we had LQG problem, which means in our state dynamics, we had a term, this is the core term, then I might use some other variables at this point. I don't remember the exact ones. UK, WK. So in the LQG problem, what will happen is this is linear, the cost is still the same one, the cost that we have seen so far, the quadratic cost. If these two become Gaussian, and obviously mean zero Gaussians, and if they're independent of each other, and the zeroth state is also some Gaussian, then the remember when we talked about this part, when we talked about the optimal action in LQ problems, we made no assumptions about what the noise was. Meaning, if we choose a specific noise, this still holds. There's nothing that's stopping this from holding. So, even in the LQG problem, the optimal strategy or the optimal action would be something that has dependence on LK, the Kalman gains. That's as it is. And this particular term. Now, because we are specifically in the regime of Gaussians, this estimate actually ends up becoming linear in IK. You could write this out carefully and see that this is actually Gaussian. Sorry, this is actually linear in IK. The conditional expectation of a Gaussian has that strict form. So, what happened here is, in this whole comparison of LQ and LQG problems, we managed to put a restriction on the noise and got a simpler result as far as the optimal actions are concerned. The optimal actions become linear. Now, what this is telling us is, in LQ games, if we could find this mean quantity, we were done. Same thing here, if we find this mean quantity, which we know is something that is only linear in information IK, then we are done. Meaning that there is something coming up here, that there is something called a sufficient statistics. If we know this much about the state, we are good. We don't need to keep all the information, right? So according to that, this term is serving as a sufficient statistics, meaning this much information is sufficient to know about the state of the system. We don't need to know everything. We don't need to have the full history of uh, observations or actions and all of that. A part of that statistical information is enough for us to choose the optimal action, for example. So, the next question is, in this kind of a problem, we have a sufficient statistics. What happens in other problems? So, what if we have a problem which is not LQ? Can just the mean be a sufficient statistics? And we already have a rough answer to that. Remember in the very beginning, when we were talking about lottery systems, scalability of lotteries and all that, a simple lottery and versus a lottery on buying a house. So we saw there that just the mean is not enough information. At times we need more. At times we might need the next variance, the next moment, maybe the variance, maybe the third moment, fourth moment, and so on. So, is there a point where this whole thing stops? Is there something like a universal sufficient statistics that is enough to know about IK, and we don't need to keep all of that information with us at all times? That we know this much is enough. We can discard some of the information. If such a statistics exist, then our problem has simplified to an extent. We don't need to worry about our state space growing so quickly and so vast. It grows almost exponentially, right? If we're talking about IKs, IK gets added with two more information, a tuple of information every kth point, meaning it's growing quite a lot and it's growing quite fast. So, is there something called a sufficient statistics in general? So, like here, first moment may not be enough, second moment may or may not be enough, third, and so on. Same thing will happen. But there is something which is this, the whole distribution, all of the moments together, meaning the probability of xk being some x given the information ik. This could serve as a possible universal sufficient statistics. Especially in problems with partial information. So now we are getting into the whole idea of sufficient statistics and whatever it leads to. Oh, okay. Okay. So next thing to worry about is what is this quantity? This what we're calling as something that can serve as a sufficient statistics for most problems in general. So notice this is some sort of a probability this is not some, this is a probability distribution on x case, knowing whatever information we have up till that point. This is at times called the belief state, or just it's called the belief. It's like saying, based on whatever I've seen, what is my, what do I think is the actual state x. So I'll be saying, okay, with I think 50% of the times it must be this, the other 50% of the times it might be this. This type of a situation where we're creating beliefs about what the true state is based on what we have seen, this is referred to as a belief state. And the whole problem of POMDP, partially observed MDPs, can be modeled using this belief state. And in the process of doing that, a few things happen. We reduce the problem in one form and the complexity shifts to something else. So let's go through this portion now. So, in general, we have seen that the optimal control, the optimal action will depend on the information available. It might, for example, in an LQ problem, it might depend on the expectation of xk given ik. In LQG problems, it might just depend linearly on ik. But in general, it will be some function of ik itself. And this whatever this is, whatever function of ik it is, that's going to serve as a sufficient statistics. So the universal sufficient statistics that we are actually going to talk about is this. Xk given the information ik. So now let's talk about a general partially observed MDP, and then, like I said, this behaves like a state. This is in fact called a state only, it's a belief state. So how can a belief state be used, and how can a belief state be used to convert an MDP to a different version? That's what we're focusing on right now. So let's take a simple version of a POMDP and then do the conversion. So let's say we have a POMDP with state space S. Actually, let's be more specific. Let the state space be something like this. Let's say there are L number of states. Then there is some action 1 till U, some action space. Notice I am restricting the problem to the situation where x and u's are both discrete and finite. What is j? So there's going to be some cost. So there'll be the stage wise cost and some terminal cost. Then there'll be some transition probabilities. Oh, sorry, that's not j, that's y. Observations. So some observations 1 to y. That's the observation space. This is the transition probability. So the transition probability is action is u, the initial state is I, and we're going to the state j. Or if I were to write it more carefully, xk plus 1 uk is u. Then what is the probability of seeing an action, seeing an observation yk given the state was I? And there'll be some cost. So the cost will be a stage wise cost. Let's call that ck, something that depends on xk and uk, and the terminal cost cn of some xn. And in general we'd be taking a sum over all of these, so starting from k equal to 0 till n minus 1, and maybe there's an expectation over all of this, or maybe there isn't. We're not worried about that part that much. Okay, so right, obviously if this is our setup, we also have the information. The initial information is some distribution on the state space, some pi 0, and then onwards there is the actions and the observation. Actions and the observation. The goal of the problem is to choose the action so that the cost is minimized. So okay, let's take an expectation. And let's assume that we're starting from some prior, right? Pi 0 refers to a prior now, not a policy. The prior meaning, we're talking about how is the, in which state are we starting, what is the probability that we are starting in that particular state. That's roughly the initial prior that we have. So pi 0 is that, or this can be thought of as the belief state. There's no prior information up till this point, so this is just probability of x0. In general, the belief state would be defined as this quantity. Probability of xk being some value I given the information ik, and it's denoted as pi k of I. Notice the distribution is on the state space X, and let's say the policy that we're talking about, uh, the policy notation is these mu's. So now we are trying to write the same problem, but in the language of belief state, in the language of this. If that's what we're trying to do, we'll have to make some changes to the cost itself. The cost has dependence on xk. But remember, our estimators are quantities like this. Quantities like this are actually unbiased estimators, meaning if I take the expectation of this, an outer expectation of this, all I'd be left with is the expectation over just xk. That's what I mean, that this is an unbiased estimator.
But that was you mentioned it is what linear system, right?
Huh,
But POMDP could be anything, right?
sure.
Then
This is a property of expectations also, right?
correct, but unbiasedness could be a question.
Okay, fine. Then think of it just as a property of expectations itself. That you could take expectation over something and it changes. So this is
Yeah.
like saying,
And the second variable, if you take yes, the expectation on different variables. Yes.
this is just.
Mm-hmm.
Hmm?
Correct.
So we could write this abort term in a slightly different manner. So whichever one you're more comfortable with. Um, let's write this carefully. Because of the possibility of linearity of expectation, I'm taking this part out already. Otherwise, this should have been inside. So let's say there is an expectation of this. The outside expectation stays the same, okay? That's overall conditional. So if there was an overall conditional with some z, that would stay the same. That's what I mean here. So this is extra stuff. Okay. Now we've simplified it a little bit, but we still need to simplify it a bit more. Now the belief state is starting to show up a bit more. So if we were to write this out again, remember xk had finite discrete values. So I should rather write it as I. And here I'm taking an expectation, and there is a conditional on that. That means I'm basically invoking pi k of I, which becomes and you're just summing over I, whatever is the number of states. So maybe, yeah, maybe let's say it's from 1 till n. The k component is as it is outside. And similarly, the other one will become cn xn taking certain values and yk taking those. So something like, and this is the prior that we're starting out with. That stays the same. Then notice this is more like a inner product term, and so is this. So we could define this and this as some vectors. This is anyways a special vector, which is like a vector in the simplex space, but this is a normal cost vector. So if we define this as cu, some action u, and take the inner product of these two, we would get the following. And similarly over here. So we have first, for our first step, we have introduced the state in our cost function. Now next step is there should be some dynamics, but the dynamics component is very easy. Remember, we already had this this observation, an earlier observation telling us what the dynamics is like for this pi type things. So exactly same thing will apply here. So this belief state pi of k will depend on the previous state, the observations, and the actions taken in the previous step. Notice in week 4, we didn't worry too much. Here, we didn't worry too much about the action. We were only focused on finding this quantity. Now, we need to also have the dynamics included with the action component as well. And if we do that, it's exactly these terms that show up. What we get here is b this byu is the diagonal with the bij, the biyu we saw earlier. So this is a matrix where you're putting these entries in the diagonal. P t of u, p of u rather, is the transition matrix. All the transition probabilities put in the form of a matrix, a doubly stochastic matrix. Okay, what is this pi? Oh right, this pi is the exact same one that we had up till here. So this pi refers to pi 1, pi 2 till okay, do you recall what was this pi?
Which one?
This.
It was a vector actually.
But what vector of what?
Mm, as far as I remember, it was the value because pi k of I, right?
Ah, right, it's for all the n values, right? So
And in terms of conditional distribution, the x value, what x can take, basically state.
pi of 1, pi of 2 till pi of n, because x can take values between 1 till n. Yeah. And lastly, this sigma is just sum of all of these things. Summed over all x. So if this was written in the k form, so this is all the x values, so from I equal to 1 till n. So all of those, the vector, this should give us a vector in the end. So just a sum over all of that. Sorry, this was transpose. So this is pretty much the same form as here. The only difference being the action component is very carefully incorporated as well. So now what has happened is we managed to go from a POM DP, a partially observed MDP, to a situation where we have a cost function, which is a fairly simple cost function, and we have some dynamics equation. So this is converted into a simple MDP. But the catch here is this pi is actually now some sort of a vector, some correct dimensional vector. So if these are n dimensional objects, so n dimensional object such that the sum of all of these, each one of them individually, is greater than 0, and sum of all of those i's, let's say this is the set of states now.
Oh, what I do is I just do underscore some line or upper score line to mention that.
Where?
Uh, like this is a vector or this is a matrix. So just underscore by a line.
Ah, oh, okay. Okay, it's fine. Anyways, I'm
But
defining a set now. This becomes the belief state, the set of belief states. But notice these are n dimensional vectors, and each of
mm,
those vectors can take any values. There's no restriction on the values as long as these two conditions are satisfied. So now it's no longer a finite state space. The state space has increased from finite to something which is infinite with some restrictions on it, but still infinite.
this expectation and costs, right? When you go up.
Yeah.
So as far as I remember, the expectation mu, since x is not, we are talking partially observed. So x also will be the expectation part, like the outer expectation. I'm talking the bit mu, right? You have mentioned. Now it was since x is partially observed, so it was the x part also. Now we have removed the x and introduced the pi.
Hmm.
So is that the pi also will get basically across this set should be some other distribution or
We're
what?
already doing that. See, we're already taking an expectation with respect to pi. pi is a distribution, right? We are
Hmm.
already taking an expectation here. It's this expectation. We're
Huh.
already incorporating that effect.
This is what the conditional one. The outside expectation of mu had the x also. The outside one, yes, yes. This one has a mu and x. If you go with a partially observed formulation, the
Mm-hmm.
cost to define whatever, because x is unknown, right?
Yeah, x is unknown.
So we have given expectation over x, omega, and all those things at that time.
Hmm.
So if I formulate similar to this here, x also will come. Now, if I replace with pi, then pi should come there, which means the set capital pi
Hmm.
across that I should have some kind of expect. I may wrong. I just I'm making connection with the previous one.
So what is happening here is, see, typically we have an option. We don't always have to take expectation with something that is hidden. We could just take the value. So we can think of the cost function to be something like a black box. We don't know this, but the environment does. Right? The environment knows the true state. It can use that information to come up with the cost. The cost doesn't have to be something based on a quantity that is observed, and hence the expectation always doesn't have to be always dependent on that x. Are you following what I'm
Mm,
saying? So both of those ideas are actually fine. You could do the
same.
same thing for pi also. It's fine.
But this same thing I can say environment knows about my action. So environment is a black box. I can the same argument can true for action also.
It
But
can, it can.
like something is I'm feeling this what is it? This set you define at capital pi.
Hmm.
That capital pi, if we introduce a distribution across, which is a continuous distribution, that distribution we should introduce there to with mu.
But this is already a distribution, and we've already
So
taken care of
distribution
it.
over distribution, like kind of thing is coming.
Okay, think about it this way. We are already taking expectations with respect to pi k. We could potentially write it like this also. This is a little tricky. You could
Yes,
potentially write it
we
like
could.
this.
I'm not able to visualize this part because my brain is telling pi. Where is pi missing outside?
It could
We
be something like this.
somehow finite state to infinite we are going. Don't know. I need to check something.
Something like this can be done. But this is to be done very carefully because something like this, but this is actually not correct right now. But
Yes, yes,
it
yes,
can be
yes.
done. Now, here pi means pi 1 till pi k. And if there's no dependence of a particular pi in any of the terms, that will just be summed over all of it. So that will just be 1. So it will, these two will become equal
Okay.
till n actually.
Mm-hmm. Fine. I need to search more on this.
Hmm.
Yeah, you can continue.
Yeah. So now what this is telling us is that we started out from a partially observed MDP and got an MDP where the state was a belief state, right? Our state space, which was originally X, now got converted to this funny looking pi. Our action space did not change. I don't know what symbol I used for action, maybe U. The action state is still the same. There were observations. There are no observations here. It's perfect information now. We had some transition probabilities P and observation probabilities B. Those got converted into some sort of a dynamics. So this P T depends on P, B, and U all. So some dynamics is what it got converted into. You could convert this dynamics into actual transition probabilities as well and write this as some p dash. That is also doable. It's completely valid. And the cost also, we managed to just convert the cost a little bit. But the key point here is originally there were observations, and the state of observation was obviously the number of observations made at any point of time was getting more and more. The information available at any point of time was getting more and more because at every step an observation would be made, an action would be taken, and so on. But here now we're in a situation where there is no information, there's no hidden information, it's perfect information available. And we managed to convert our problem from POMDP to MDP. The only catch is now instead of the actual state, what we are defining as a state is a belief state. And this belief state is infinite dimensional. It has some structure on top of it, but it's still infinite space. And this can be concluded in the form of a very nice theorem, which says that the minimum expected cost, let's say, is achieved by a policy. Then this policy will now depend on the state pi k meaning our belief. And since we were saying that this belief is like a sufficient statistics, this is enough to actually get us the optimal actions also. And we can find these optimal solutions using the same process of DP, meaning we start from the last step and go one step backward at a time and solve for this type of a situation. So this is basically like a complete roundup, wrap up of whatever we have seen so far. We started by talking about simple MDPs and stochastic control problems. Then we went to, then we took the situation of linear quadratic problems. There we saw a lot of interesting behavior. We saw that the optimal, if it is perfect information, then the optimal is just linear in the state itself. The optimal action is linear in the state. Then if we extend our problem to the situation where we have some information is missing, meaning there are some observations made and that observation is made available to the next one, then the optimal action becomes related to the mean of the state given the information. And that is what led us to the idea that that is like a sufficient statistics for LQ problem. In LQ problem with imperfect information, then in a general imperfect information problem, a general POMDP type problem, we can say that the sufficient statistics could be the belief state and convert the POMDP problem to a MDP problem. And to solve this MDP problem, we have to follow exactly what we did in DP algorithm, like a standard MDP problem. The conversion, the cost of the conversion comes in the form of pi k. Now, all of this needs to be done for every pi k, and pi k is no longer finite. Pi k is not coming from a finite space, it's coming from an infinite space. That's where the complexity lies now. Otherwise, we have managed to cover the core types and classes of control problems. There is definitely a lot more to come in the further weeks, but this is the point where the ideas in the course will shift a little bit. Now onwards, the focus is going to be more and more about information. The belief state sort of wraps up everything that we have seen so far in stochastic control.
Information about
What information is available to which agent at what time. So there are different ways in which the information could be available. depending on how the information is available, a lot of interesting behavior comes up. But that's called information structure.
Okay.
I remember in the beginning only, this was again in the very first lecture, there was this point: if an agent knows something about the action, it will choose its actions in a sequential manner. Then the behavior is different, versus when there's no such sequential behavior and you have to take your actions just at the same time. Then the choice is different because the information in the two problems is different. So those kinds of scenarios will be now studied more carefully. Up till now, when we were saying information, we were just referring to observations and actions. Now there's going to be more structure in how the information is available and what else happens to it.
Okay. Out of those reference book, which one contains this information structure?
uh, which are the reference books you're following?
In that portal, Swam portal, there are some 7, 8 reference books.
um, if I remember correctly, information structure comes up in Witzenhausen's paper, and what is this team theory paper by Ho et al. Those are the standard references. I'm not sure what sir is using. I'll have to check that. I'll tell you next time, because that's when information structure and so on will start.
Yeah. Fine.
But if you want to refer to something, refer to these two papers. I think these two papers are mentioned in the references also. These are like
Oh,
classic papers.
okay.
Witzenhausen's counterexample to, so the counterexample basically goes into this idea. We have been saying, right, if it's a LQG problem, then we're going to have linear, as the optimal action is going to be linear in the action or the belief of the action or some moment of the belief of the action. But Witzenhausen is going to give a counter example to that, and to give the counter example, he will change something about the information that is available. So that's what is going to come up in the upcoming lectures and so on.
Sounds very interesting.
Yeah,
And for
it is.
this wrap around, do we have any example? Like, how do we utilize this? For example, climate change condition. Let's suppose this example. If I take, I have some states, finite state, like going down and down temperature, or going up and up.
But
Now,
temperature is not a discrete quantity, it's a real number. Take something
okay,
which is, 1 2 3 4, like discrete, genuinely discrete, so easier to handle for you.
okay. Let's say Himalayan ice amount, but that is also not discrete.
Mm-mm, that's also not discrete. uh, Go back to the inventory control example.
Okay. So
So
if we don't know the inventory current state, then
yeah, so remember, while we were talking about inventory control, we had this assumption that whatever we have ordered will arrive within the time period. So between k and k plus 1, that thing would have already arrived. In reality, that's not what happens. So at any given point of time, we don't know where the inventory has reached, or whatever we are ordered, where it has reached, and when will it arrive. So what is going to be our current state is going to depend on what is known right now, but it might change at any point during the discrete time period that we have chosen. So it can be roughly thought of as a problem with information being important. Or what were
okay.
the other examples that we had with imperfect information?
At flight control also.
Hmm. Flight control, yeah. Okay, so what do you want to do? You want to think of belief state in that, but
Yes,
flight
yes, yes,
control,
yes, yes.
the this it the state space consisted of position, velocity, and orientation, stuff of that kind, or the The rate of change of orientation. All of those are real numbers. You need something which are not real numbers and imperfect information type problem.
Need to think more on this because this is very
This is very
like
specific.
the idea is very different and very eye opening. But where
Hmm.
to apply, where to think.
Hmm.
Okay, thank you.
Yeah. Let me quickly summarize what we talked about today because next week onwards it's gonna shift a bit. So we started by okay, before even where we started. So in the previous week we had talked about the separation between the estimator problem, the estimation problem, and the controller problem. So first we spent some time talking about one kind of estimator problem where the noise is taken to be Gaussian. If that happens, then this type of a problem is called Kalman filtering. So in Kalman filtering, we saw what the algorithm is, and the algorithm basically has two steps. First is the prediction step, and the other is the measurement step. Then we used something called the Swiss Army knife of Gaussians, a property of the Gaussians, which allows us to get the value of mean and variance of the next iteration in a recursive manner. Because of this recursive property, it becomes easier to handle all of these, and it can be converted into iterative algorithm and actually used to solve problems. This was just one example you could try out for a coding scenario. Then we tried to extract information from all of this. So in LQ, we saw that the optimal action has dependence on the expectation. Oh, the expectation, the mean of the state given the information. In the LQG problem, on the other hand, this mean given the information becomes linear in the information itself. Meaning, depending on which problem we're talking about, something might be enough to describe everything in the problem, including the optimal actions. And that is what is referred to as sufficient statistics. We're claiming that one possibility or something that is like a universal sufficient statistics is instead of taking one moment, first moment, second moment, and so on of any distribution, let's just take the whole distribution itself. So, this is the distribution of x given the information, xk given the information. And with this idea, we converted a partially observed MDP, to be specific, a partially observed MDP with finite state space, to a problem with a normal MDP where the state is the belief state. The only thing that changes between this POMDP and this MDP is that the state space, which was originally finite, has now become infinite with some more conditions, some more structure on top of it. And since there was some observations before, because it was imperfect information, there are no such imperfect information problem. It's just a perfect information problem, a normal MDP. Hence, it can be dealt with just like a standard MDP, meaning we can find the optimal policy, and that optimal policy can be something that will be related just with the state. Remember, we had already proved that state is enough information. We don't need to go to histories. So that's what is something coming up again in this point. And then even with this belief state type of situation, we can use DP algorithm and find the J values, the Bellman values. And once we have found all of them, we can also get the corresponding uh, optimal actions as well. So this is like a full wrap up, full summary of all the things that we have done in the context of control, and that as long as we're working with the MDP formulation, there are a lot of different versions, different classes of problems that can be reduced to an MDP, and then it's very easy to work with MDPs further on because of the presence of this DP algorithm. So a lot of things have actually converged to being an MDP. That's like the takeaway, that if you can formulate a problem with history, with information, and using one or the other technique, bring it back to being an MDP. We can just use a DP algorithm and it becomes solvable. It becomes something that can be handled. May or may not be tractable, but definitely in practice we can solve for it. We can at least try for it. That's the uh, wrap up of this portion so far. Okay, so yeah, this is from my side. Do you have any more questions?
No.
All right, chalo, let's wrap up here then. Thank you so much.